Hello, chemistry students. Today we're going to talk about topic 1.5, the atomic structure and electron configuration. You learned about this in first year chemistry for the most part, so this is review. All right, so you need to be able to represent the electron configuration of an element. Just as a reminder, electron configuration is something that looks like this: 1s2, 2s2, 2p6. I'm hoping that draws back some memories. 3s1, something like that, of an element or ions. Okay, so you need to be able to do both, and I'm going to show you how to do both. Of an element using the Aufbau principle. All right, so basically the Aufbau principle says that you need to fill up the lowest energy level first. Okay, fill up lowest energy level first. And we're talking about electrons. All right. Okay, we'll get to that in a little bit. So first qualifier, it says an atom is composed of negatively charged electrons. I denote electrons with a lowercase e with a superscript of a minus sign. And positively charged nucleus that is made of protons and neutrons. The protons and neutrons are in the nucleus. Okay, protons I denote with a lowercase p with a positive sign for a superscript, and neutrons are lowercase n with a 0 as the superscript. All right, so I don't like to write all that stuff. All right, so it says draw a Bohr model of the magnesium 25 atom. Be sure to include the correct number and relative positions of the protons, neutrons, and electrons. I'm surprised I didn't write electrons there. Sorry. I should have. Change that for next year. Okay. All right. So just as a reminder, when we have, this should say magnesium dash 25. I had the wrong number there, so I had to correct it. It should be correct on yours, though. And it is. This is the mass number. And a mass number is the number of protons plus the number of neutrons. All right. These are the two subatomic particles that make up the mass of an atom. All right. It takes approximately 2,000 electrons to equal the mass of one proton, which equals the mass of one neutron. All right, and there is no atom that has even close to 2,000 electrons in it. So electrons are negligible as far as mass is concerned. All right, and this is mass. I'm talking about mass here of each of these. All right. All right, so the electrons are not massless, but essentially compared to the protons and neutrons, they are. All right, so magnesium. Let's look at magnesium on the periodic table. Magnesium is right here. Okay, the number of protons is denoted by the atomic number. Okay, and that is equal to the number of protons. Okay, so magnesium has 12 protons. And in an atom, not an ion, but in an atom, the number of protons equals the number of electrons. So we also have 12 electrons. Okay. All right, so in this magnesium atom, we have 12 protons, we have 12 electrons, and we know the mass number is 25 right here. And the number of neutrons plus the number of protons is equal to the mass number. All right, so let's go ahead and figure this out. So 25 is equal to the number of protons, which is 12, plus the number of neutrons. So if we do some algebra here, the number of neutrons is going to equal 25 minus 12, which is equal to 13. So a magnesium 25 atom has 13 neutrons. All right, neutrons and protons are located in the nucleus, and this surrounds the nucleus, the electrons. All right. Okay, so let's pick some colors here. We're going to choose green for neutrons, and we're going to choose red for electrons, and how about blue for protons? All right, whoops. Blue for protons. Okay, so we have 12 protons, so I'm going to draw a Bohr model. Okay, we got 12 protons. One, 2. Let's make this a little thicker. Three, 4, 5. Why did I feel like that was not very thick? Because I didn't press OK. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right, and now we'll do 12 electrons. I'm sorry, 13 neutrons. One, 2, 3, 4, 5, 11, 12, and this is about 13, okay? So we'll just pretend. All right. Okay, now the electrons orbit the nucleus, okay? And we have our first energy level here where the electrons go. And then let's go ahead and draw our electrons. So that should not be that. We've got a dot here and a dot here. And then we have another, I don't know if you guys remember from last chemistry class, that our electrons, the inner energy level, or energy level 1, can only hold 2 electrons, and the other energy levels can hold 8. I'm going to show you on the periodic table why that is. So 1, 2, 3, 4, 5, 6, and we've got a total of 12. So 2, 4, 6, 8, 7, 8, and now we've got a third energy level. And we've got a total of 10 electrons right now. So those last 2 are going to go in the third energy level. Now let's look at the periodic table, because I wanted to show you something. Magnesium is right here on the third energy level. Whoops, I didn't mean to do that. It's the first energy level, the second energy level, and the third energy level. So if we look at this, the first row, or the first energy level, can only hold 2 electrons. The second row, or the second energy level, can hold 1, 2, 3, 4, 5, 6, 7, 8 electrons. Third energy level, up to magnesium, only needs 2. All right, which is why we have 2 for the first energy level, we have 8 on our second energy level, and 2 on our third energy level. This would be the Bohr model for the magnesium 25 atom. All right, our nucleus, or most of our mass, is in the center. And by the way, this is not to scale. Okay, now let's go to the next problem. It says, using Coulomb's law, we're going to use this Bohr model up here for this. Using Coulomb's law, calculate the relative forces. I really don't like where it says calculate, because we don't do that. Calculate the relative forces to remove an electron in the second energy level. So we are looking at n equals 2. And by the way, this stands for energy level. All right. And that is that energy level right there. Okay. remove any one of those 8 dots, or electrons, from the second energy level in a magnesium 25 atom and an electron in the first energy level. So N equals 1 is the first energy level, and that is the one that's closest to the nucleus. All right, in a magnesium 25 atom. Calculate the relative forces to remove an electron. There shouldn't be a question mark here. All right, which electron would require more energy or force to remove? So this equation right here is given to us. It is called Coulomb's law. I'm going to zoom in on this. And it is a force that is, this is a proportion symbol. Proportional or proportion symbol. Q1 is a charge. Q2 is another charge. And depending on what you are talking about, these charges come from different things, okay? Right now, we're talking about an electron and a nucleus, okay? And the nucleus charge is denoted by the protons, because neutrons have a neutral charge. They have no charge. All right, so one of these Q's is going to be the electron that we remove, and the other Q is the charge of your nucleus, all right, or how many protons you have. For this unit, that's what it's going to be. For another unit, we're going to be talking about ions and their charges and their ion size. This right here looks like radius. It is the distance between the charges. All right. Okay, so the distance that separates those charges. Okay. I'm having issues here. Okay. All right, so what we're going to do is we're not going to actually calculate these. I'm not really sure why they say calculate here, because you're technically never asked to calculate using this formula, using Coulomb's law. You're just asked to compare, all right? So in energy level 2, let's go ahead and talk about that. So energy level 2, the force is going to be proportional to, our Q1 is going to be 1 electron, since we're removing 1 electron, and we're removing it from the thing that keeps it attached to the atom. And the only thing that keeps this electron in energy level 2 staying in this atom is the protons, okay? And there happen to be 12 of them. So we're going to use 12 right now. Later on, we're not going to, but for now, we're going to. All right, and that's divided by some distance, r. Okay, and we're going to square it. We don't know what that distance is. N equals 1 on energy level 1. Our force is going to be proportional to the charge of an electron times the charge of the nucleus, what keeps it attached to, or what keeps it inside the nucleus, or inside the atom, I apologize. Okay, and that is the same, okay, and the r squared. Okay, so here's the caveat. Right now, we don't know what the distance is from this nucleus, and, well, I should use a different color, from this nucleus and that electron. We don't know what that distance is, nor do we know what this distance is from this electron to that nucleus. But what we can do is we can compare the two things. All right, so the distance between the nucleus and energy level 1 is less than the distance between the nucleus and energy level 2. All right, so this distance is larger than that distance. Okay, and because this the energy level 2 distance is larger, if you have a larger number in the denominator, that is going to cause this Coulombic force to be smaller. than this Coulombic force. Okay? If it's less of a force, it's going to take less energy. All right? So but basically, if this would be like a free response question, you would have to write Coulomb's law and then write the charges and then say that the distance in energy level 2 is greater than the distance in energy level 1 of an electron between the electron and its nucleus. And therefore, because the distance is larger in energy level 2, between the nucleus and the electron that's going to be removed, the force would be smaller. Okay? Which electron would require more energy or force to remove? An electron in energy level 2 takes less force, but this is asking which one requires more energy. An electron in energy level 1 will require more force. And therefore more energy to remove. Okay, so you've answered the question. Now you have to justify it, because the distance between the electron and the nucleus is less than, and the nucleus in energy level 1 is less than the distance between the electron and the nucleus in energy level 2. All right. According to Coulomb's law, since you have to justify it via Coulomb's law, we're going to say a smaller distance. You could say a larger distance requires less force or less energy. A smaller distance between charges requires less force, or requires less energy, I'm sorry. Requires less energy to remove. All right, so on a justification, you must answer the question, and then you have to justify it. You can't just justify it any old willy-nilly way. You have to justify it the way the question's asking you. And here it says using Coulomb's law, so you must use Coulomb's law. You must, okay? And here's the equation for Coulomb's law. All right, let's move along. Okay, so in atoms and ions, the electrons can be thought of as being in shells or energy levels, just like we did in the Bohr model above, in subshells or sublevels, as described by electron configuration. Okay, so your energy levels are your n equals 1, n equals 2. Excuse me, in an electron configuration, these, your energy levels are your coefficients, okay? Oops, let's see here. These are our energy levels. The subshells are the P's and the S's, okay? Those would be your subshells. S, P, D, and F. And your energy levels are 1, 2, 3, and 4. And 7 goes all the way up to 7. 2, 3, 4, 5, 6, and 7. Okay, and your subshells or sublevels are SPDFs. As described by the electron configuration, inner electrons are called core electrons, okay? And outer electrons are called valence electrons. So let's look up here at our Bohr model. I am going to highlight our core electrons as yellow. So anything that's inside the outer shell will be your core electrons. All right. So maybe yellow wasn't the best choice to do. So I'm going to go ahead and do this with, these are core electrons that are yellow, okay? And we'll denote the outer shell electrons as green, okay? Or valence electrons, okay? And your core electrons are right there, okay? And right there. Okay. The electron configuration is explained by quantum mechanics as delineated in the Aufbau principle and exemplified in the periodic table of elements. Okay, we're not getting into too much of the quantum portion in first level chemistry. Okay, we're only getting into the Aufbau principle, which says that lower energy levels are always filled first. So you're not going to have some electron way out in the 7th energy level in a magnesium atom. And so here we have in our magnesium atom here, we have 3 energy levels. We're not going to have, let me go ahead and show this. So if we have number 4, number 5, number 6, and number 7, we are not going to have an electron way out here. Okay, we're just not going to, unless we add a whole bunch of energy, and then that electron won't stay there for very long. Okay, electrons always have a tendency to go to the lowest energy level state. So you're not going to find one there, according to Aufbau principle. Lower energy levels first. Okay, so assignment of quantum numbers in subshells will not be assessed on the AP exam, so you don't have to worry about that. Valence electrons are your outer shell electrons. These are the ones that participate in the formation of a chemical bond, okay, if the outer shell is not closed. And what this means is if it's filled with maximum number of electrons. We'll get more into that later, okay? All right, core electrons. Those are the electrons in an atom that are not the valence electrons. So every single electron that is in a lower energy level, okay? They do not participate in bonding, all right? So let's go back up here and look at our Bohr model again, all right? So the only electrons that are involved in bonding are these outer ones right here, your valence electrons. The yellow ones are not involved. Ever. They don't even touch another atom at all. It's just these outer ones. Okay, Aufbau principle. In the ground state of an atom or ion, electrons fill atomic orbitals of the lowest available energy levels. Okay, that means energy level 1, energy level 2, etc. Okay. These electrons that are in energy level 1 don't have very much energy. Okay, they can't get away from, they don't have enough energy to get away from the nucleus. Okay, unless you add a lot of energy. So a ground state means that it is not excited and you haven't added any extra energy. Okay, to those electrons. Okay, your electron configuration basically tells you the address of your electrons. It's the distribution of electrons in an atom or molecule in the atomic or molecular orbitals. Shells are energy levels. It is denoted by the variable n. It tells you how far the electron is from the nucleus. The larger the energy level value, n, the farther away it is from the nucleus. So n equals 1 is the closest to the nucleus, closest. and closest and farther away is energy level 2, okay? And this is to the nucleus. All right. Okay, your subshells or sublevels are SPD and F. They are levels within an energy level or shell. Okay, and they must have the energy level as a prefix. So that's the energy level, and then that's your sublevel right there, the NF. Okay, the F. N denotes the energy level 1. Okay, this is your sublevel S. All right. Or your subshell, that's technically your orbital. Your subshell is 1s, or sublevel. Yeah, okay, so I'll explain this more when we do our electron configuration. Okay, so I have color-coded this for you, and as a reminder, when you do your electron configuration, your s orbitals are the green, all right? And your p orbitals are the blue, d orbitals are the red, and your f orbitals are your yellow. All right, the energy levels are what period you're on, or row. Okay, so when we write electron configuration, we're going to do bromine, and bromine is right here. Okay, so when we do bromine, the very first thing we're going to do for a complete electron configuration, it's like reading a book. Right? We're going to start at the top of the page on the far left, and then we're going to go to the right. So we're going to start right here, and it is energy level 1, and we are going into sublevel S, and then I'm going to start counting. So I've got 1, 2. I just counted all the way across the row. Now I am leaving energy level 1. Okay, so I'm going to put a 2 there. So I've started at hydrogen, and I've gone all the way across, and I get to 2. Now I've finished that row. I'm going to the second row, which is energy level 2. So I'm going to write a 2 here. I am entering into the S sublevel, and I'm going to start counting. So I go through lithium, and I go through beryllium, and that's 2. Lithium and beryllium, that's 2. So I am leaving the sublevel 2s. I am not done, so I'm going to keep going across here because row 2 is not done. And I am going to enter energy level 2, sublevel P. So I'm going to write 2p. And then I'm going to go through boron, carbon 2, nitrogen 3, oxygen 4, fluorine 5, and neon 6. And I am leaving the 2p. So I'm going to put 6, because I went through 6 blocks up here. I haven't hit bromine yet. So now I'm going to go on the third row. Okay, so I'm going to put energy level 3, sublevel S. I'm going to count through sodium and then magnesium. And then I leave the 3s. So that's 2. So I'm going to put a 2 in front of my, as a superscript on my 3s. I'm not done yet. I have not hit bromine. So I'm going to go all the way across. I'm still on energy level 3. And I go to aluminum, and I'm entering into the P sublevel. So I'm going to count. I go through aluminum 1, silicon 2, phosphorus 3, sulfur 4, chlorine 5, argon 6, and then I leave the P sublevel with going through 6 blocks. Still haven't hit bromine, so I got to go to energy level 4. So that's what I'm going to do, and I go into the S sublevel. All right, I'm going to go through potassium, then calcium, and then I'm leaving the S sublevel with 2. Okay, once we get to the D sublevels, it does something funky. All right, so our energy level actually decreases by 1. We're on energy level 4, but we subtract 1 from that, and we're on energy level 3. Okay, don't forget to do that. So this is 3, and I'm entering into the D sublevel, right? I'm in 3D, 1, 2, 3, 4, 5, 6. I'm at iron now, 7, 8, 9, 10. I've gone through zinc, and I've gone through 10 blocks. Okay, and I'm exiting the 3D. So I'm going to put a 10 there. I am now entering the 4th energy level, P sublevel. So we go back up to 4 and then D. All right. I'm at gallium, Ga. I'm going through gallium, germanium, that's 2, arsenic's 3, selenium's 4, and now I've hit bromine, that's 5. Okay, and then I stop because we're looking for the electron configuration for bromine. So this is the complete electron configuration. Okay, and the reason we call it complete is we started at the 1s. All right. Okay, but if you look over here, the answer doesn't look like that. We have argon here. So if AP does not ask you for the complete electron configuration, they just ask for an electron configuration, they will accept a noble gas electron configuration, and that's what this is. So as a reminder, everything in group 18 is a noble gas. So how you would do that is if you have bromine, what you're going to do is you're going to go up 1, and then go to the noble gas, which is right there, argon. Or you could think of it as I'm going to the noble gas before bromine, okay? If krypton is the noble gas after, then argon would be the noble gas before. So we would write argon, and we put it in brackets. You have to have brackets. And then you start on the same energy level that bromine is on. So let's go ahead and start, and I'm going to use a different color. Let's use purple, okay? So I'm going to start right here, all right, on energy level 4, which is the same energy level that bromine is on. So I'm going to say 4. I enter in the S, and I count 2, potassium and calcium. So 4S2. I am now entering into the 3D. Don't forget, D's, you subtract 1. And we're going to go all the way across. There's 10, so 3D 10. And now I'm exiting the 3D10 and going into the 4P. So I'm going to write 4P here. And then I'm going to count till I get to bromine, which is 5. 4P5. All right. So if you notice, if you look at our complete electron configuration right here, this portion, the 4s2, 3d10, 4d5 is the same as this one down here, which means this is the noble gas or the electron configuration for argon. All right. Okay, so I'm going to let you guys do the rest since, well, you know what, let me show you about an ion first. And then I'll let you do the rest. Check it. If you have questions and you don't, if you can't get these electron configurations doing it on your own, please ask me in class. Okay, bromine ion. So bromine is in group 17. All right, it's in group 17, which means it has 7 valence shell electrons. Ve means valence shell electrons. Okay, now remember, every element on here will react until it has a stable outer shell. And what a stable outer shell looks like is it looks like a noble gas electron configuration. All right, so it will have 6 electrons in its p orbitals and 2 electrons in its highest energy s orbital. So bromine is going to want to look like krypton, basically. Okay, it's going to want to look like krypton. So krypton has 36 electrons in it. So your bromine had better have that. All right, or your bromine ion. Bromine ion just means that it's going to gain 1 electron because it wants to look like krypton. All right, to become stable. It needs to have a noble gas electron configuration that looks like krypton. All right, so what you're going to do here is you're going to take your argon, because we're going to be lazy and not write the complete electron configuration. So we're going to do argon, and then we're going to start at n equals 4 and do 4s2. And we've gone through potassium and calcium. Then we're going to 3D, and we're going through all 10 all the way to zinc. And then we're entering into the 4s or 4p. I apologize for that. 4p, and all 6 are filled, because it looks like krypton, 4p6. All right. Okay, so I'm going to let you guys do the rest, and then we're going to move along to one of these right here. So the core electrons for each of the above atoms, ions. All right, so remember, your core electrons are the non-valence ones. And by the way, your valence electrons are the highest energy level S and P. Okay, so let's look at bromines up here that we just did. All right. Specifically this one. So, well, no, let's look at this one. I'm going to erase all this. All right. If we look at the highest energy level for this electron configuration right here, what I'm focusing on are these coefficients. Okay, and I'm looking at the highest energy level. So 4. And I'm looking for, this should say P, not D. I hope you guys noticed that. I just caught it. Your 4s, the highest energy level is energy level 4. Your valence electrons are always in the S and P, never in the D or the F. So S and P. All right. So everything else would be a core electron. This is a valence electron. These guys are valence electrons. And you have 2 plus 5, so you have 7 valence electrons. These are your core electrons. Everything else. And that. Whoops. Core electrons. All right. And let's go ahead and count those. I'm going to highlight them for you. So we've got 2, 4, 10, 12, 22. So we have 22 core electrons. All right. Plus 7 valence electrons, that gives us a total of 29. All right. And we can look. Is that right? 2, 4, 10, 12. Oh, we forgot our 3p6. Just say, what the heck happened here? That's not right, because that would be copper. 2, 4, 10, 12, 18, 28. All right, so 28 plus 7 is 35. I hope I'm doing my math right. And 35 is bromine, because I look at my atomic number down here, and that would be bromine. All right. So if we give you an electron configuration, you should just be able to count these numbers up here, and that tells you how many electrons you have. If it is a neutral atom, that should tell you what element it is, because the number of electrons equals the number of protons. All right, guys, so I'm going to let you do these as far as the core electrons are concerned. If you have questions, you don't get the right answer, please let me know. All right, now let's go to this qualifier. So it says the relative energy required to remove an electron from different subshells, all right, of an atom or ion, or from the same subshell in different atoms or ions, which is ionization energy, by the way, removing an electron from from an outer shell is called the ionization energy, or the first ionization energy, or from any shell is called ionization, but we have to be specific on that. Can be estimated through a qualitative application of Coulomb's law. Okay, so we are not going to actually calculate anything when it says qualitative. All we do is compare. All right, the energy is related to the distance from the nucleus. Therefore, just as a reminder, Coulomb's law is the force is proportional to charge 1 times charge 2 over r squared, and that is the distance from the nucleus. Okay, and the effective charge of the nucleus. Okay, and we have shield here. So before we were saying that one of these was our charge from the nucleus. Now we're talking about shielding electrons, so we're going to be a little bit more explicit, and I'm going to explain that to you. Okay, effective nuclear charge, they do not give you this formula, so this is just something that you're going to have to remember, but this is how you would explain shielding electrons or effective charge, which is not the same thing as a nuclear charge. All right, effective nuclear charge is the net positive charge experienced by an electron in a polyelectronic atom. Poly means more than one. Electronic means that we have electrons. So we're basically talking about every single atom on the periodic table with the exception of hydrogen and a helium ion. So I'm going to come back up here to our Bohr model because I wanted to show you something. You guys should know that electrons repel each other because they have negative charges. So this is an electron, and this is an electron right here, and this is an electron. These two electrons are going to repel each other. These two right here, they're going to repel each other. Okay, so this electron right here is experiencing less force from the nucleus than this electron in energy level 1. So again, the electron from energy level 2 is experiencing less force from the nucleus than energy level 1 because it's farther from the nucleus, and 2 because there's an electron between it and the nucleus on energy level 2. There's an electron on energy level 1 that is repelling the electron in energy level 2. So the electron on energy level 2 experiences less of a force, less of a net force, and that's what the effective nuclear charge is talking about. All right, so this is how you would calculate it. Your effective nuclear charge is the nuclear charge that outer electron is experiencing from the nucleus. Z is the number of protons, okay, in your nucleus, and S is your shielding electrons, okay, or the number of electrons. We're going to call them core electrons, but they don't technically have to be core. So I'm going to say the number of electrons in inner shells, okay, than the shell that we're talking about. Okay, the shielding effects, sometimes referred to as atomic shielding or electronic shielding or electron shielding, describes the attraction between an electron and the nucleus in an atom with more than one electron, because those electrons are repelling each other to some extent. So this looks like the exact same problem that we've had before, and it is, except we're going to justify it using effective nuclear charge now. So it says, using Coulomb's law and effective nuclear charge, would the force to remove an electron in the second energy level in a magnesium 25 be less than, the same, or greater than removing an electron in the first energy level in a magnesium 25 atom? Justify your answer. So we've already determined that it requires more force to remove an electron in energy level 1 than it does energy level 2, based on the distance that the electron is from the nucleus. in a prior thing. Okay, so we based it off of Coulomb's law and distance from the nucleus. Okay, we've already done that, so I am not going to justify using Coulomb's law again. Instead, because we've already done that in our other problem, now we're going to justify it based on effective nuclear charge. Okay? All right, you need to be able to do it both ways. Okay, so let's say for energy level 2, all right, the effective nuclear charge is going to equal the number of protons, all right, and the number of protons in a magnesium atom is 12, right? Okay, minus the number of electrons in the inner shell. So we're talking about energy level 2. So let's go ahead and look at our Bohr model. Okay, so we are focusing on this electron, removing it. So we have to focus, or the inner shell or core electrons would be the ones on energy level 1. So that would be this one right here, 1 and 2. Okay, so there are 2 core electrons in energy level 2. Oops, sorry about that. Okay, and so our effective nuclear charge is going to be 10 for energy level 2. Energy level 1, our effective nuclear charge is going to be the number of electrons, or the number of protons, which is 12, minus the inner shell electrons. Now, there is no energy level less than 1. So there are no core electrons for an electron in energy level 1. So the effective nuclear charge for an electron in energy level 1 is 12. All right, and as far as Coulomb's law is concerned, now we're gonna now base it on effective nuclear charges Q1, Q2 over R squared. But right now we're gonna base it just on charges. Okay, our Q1 is a -1 for an electron because that's what we're removing, an electron, and Q2 is our effective nuclear charge, which is going to be ZF. All right. So for energy level 2, we're going to have our force is going to be proportional to a -1 times 10 over R squared. And our force for energy level 1 is going to be a -1 times 12 for R squared. So based on Coulomb's law and effective nuclear charge, not distance from the nucleus, but effective nuclear charge, and you can use Z sub EFF as shorthand for effective nuclear charge. AP knows what that means. It would require less energy, or would require more energy, either one you want to say, depending on which one you're saying at. We're going to say it requires more energy to remove an electron from energy level 1 than energy level 2, because according to Coulomb's law, okay, this should say according. Okay, something funky's going on with my writing. Oh well. Okay, you're just gonna have to rewind this to remove electron from n equals energy level 1, then energy level 2 is what this should say. I don't know what's going on here, because according to Coulomb's law, the effective nuclear charge for an electron to be removed from energy level 1 is greater than I'm sorry, and not the effective nuclear charge. The effective nuclear charge is greater. I'm sorry, I worded this poorly. The effective nuclear charge for an electron in energy level 1 is greater than the effective nuclear charge for an electron in energy level 2. Therefore, requires more force, thus more energy needed to remove, that should say remove, an electron from energy level 1. Okay, I feel like that's too many words. If you want to put that in bullet points, that would be much, much better, and that's what I should have done. We'll do that on the next one. Okay, let's go on the next one. Using Coulomb's law, would the force to remove an electron in the second energy level in a magnesium atom be greater than, the same, or be less than, the same, or greater than remove an electron in the second energy level in a sodium atom? All right, so we're looking at magnesium for energy level 2. We're removing an electron, and then sodium and energy level 2. Okay, and Coulomb's law is force is proportional to Q1, Q2 over R squared. Okay, just as a heads up, these both come from energy level 2, so our R is essentially the same distance. It's not, but as far as justification is concerned, electrons essentially same distance from nucleus. And because it is the same distance from the nucleus, we are going to focus, as far as our justification is concerned, on charges, on effective nuclear charge. Okay? Or number of protons. You can just do that too, and that would probably be a better one. All right, so let's look at that, because our effective nuclear charge is not going to be the same. Let's do a periodic table. I'm going to erase all this. Blah, 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 blah. And we are focusing on sodium and magnesium. Okay? So they're on the same energy level. Both of them are on energy level 3. This is energy level 3, but we're removing an electron from energy level 2. So we are going to focus on what's different about them, and what's different is the number of protons. Okay? So sodium has 11, magnesium has 12. So again, I want to be clear on this. They come from the same energy level. Both of these atoms are on the same energy level 3. We're removing electrons from the same energy level 2. So we need to focus on what's different. What's different is their protons, the number of protons that they have. So let's go back here. So we're going to focus on the number of protons. All right. Magnesium has 12 protons, and sodium has 11 protons. All right. So you can plug it into your Coulomb's law, and one will be about 12, and the other one is going to be about 11. Okay. So it would require less force to remove an electron from a sodium ion or atom because it has less protons. Therefore, the electron will exhibit less force to the nucleus, less of attraction. Okay? So, according to Coulomb's law, because we have to use Coulomb's law. Removing an electron in energy level 2 from a sodium atom will require less force, thus less energy needed, because sodium has one less proton in its nucleus. Okay, therefore, the electron exhibits less attraction to nucleus in sodium atom. All right, there you go. Okay, last one. Using Coulomb's law, again, Coulomb's law, with the first ionization energy, and by the way, the first ionization energy is removing the first outer shell electron or valence electron. Okay, that's what that is. That's the first ionization energy. The second ionization energy would be removing the second valence shell electron after you've already removed the first one. Okay, so would the first ionization energy of fluorine be less than, same, or greater than the first ionization energy of neon? So let's look at the periodic table, see where these guys are located. All right, so we're looking at neon and fluorine. So these two right here. So first one, same energy level. Okay. If they are on the same energy level, which is energy level 2, the distance from the nucleus will essentially be the same. And when I say this, I'm saying this loosely because it's not the same. But when you justify it using Coulomb's law, you're going to justify it whether or not it's on the same energy level or not. If it's on the same energy level, then the distances are essentially the same. So then you're going to focus, therefore, we're going to focus on charge, nuclear charge. Okay. You can either do it on nuclear charge, which is the number of protons, or you can do it on effective nuclear charge. Either one will work. Okay? Either one will work. So fluorine has 9, neon has 10, and there would be less Coulombic attraction between fluorine's nucleus and the valence shell electron than in neon's nucleus and the valence shell electron. So it will require less energy to remove fluorine's electron than it will neon's. And that's how you will justify it. So according to Coulomb's law, well, here we'll say we can just put, I'm going to do bullet points now so you don't so you can see what it looks like to justify an FRQ using bullet points. So same energy level, fluorine and neon are both on energy level 2. Fluorine and neon's valence electrons are both on energy level 2. Okay. Fluorine has 9 protons and neon has 10 protons. We are going to write Coulomb's law down. Okay, so we can refer to it. According to Coulomb's law. Coulomb's law. I'm already thinking ahead. Less force is required to remove an electron from fluorine. Let's say an electron to remove a valence electron, because we're being specific on this, to remove a valence electron from fluorine than from neon. Okay. Okay. Now, here's the deal with this. You are not explicitly stating that you have a -1 for your electron charge and your nuclear charge is 9 and then 10. But since you wrote the formula, and since you've told me how many protons there are, all right, and you've told me about the distance from the nucleus, which is energy level 2, you can make this statement right here without being explicit like we were above. Okay, that's enough. All right, so I would prefer to look at bullet points and read them, and a lot of AP readers would too. And so if you're okay with it, please do the bullet points. Now here's the deal with this. You have to say something about the energy level, because Coulomb's law has something about the distance from the nucleus. So you must state that. You must also state something about the charges, because that's what does this justification here. All right? And we are done.